Hi everyone, this is Sharif Sami, and in this video we are going to talk about CAM dynamics. Alright, pause the video and read the question 1 before we proceed.
Open your mind. Open your mind. Not literally.
Okay, the first requirement in the problem asks about obtaining an expression for the contact force and plot it against theta. So, starting from the displacement given in the figure, we can calculate the velocity by performing the time derivative, and then we can get the acceleration. After that, the contact force can be calculated from the following expression: f of t equals mass times the acceleration plus the damping coefficients times the velocity plus the spring constant times the displacement plus the preload force. And after substitution, we can get the following expression as shown in your screen. Since we are plotting the contact force against theta, it would be more convenient to rewrite the expression in terms of theta. Knowing that theta equals omega t, we can write the contact force as follows. By now, we can calculate the contact force at different angles to construct our plot. The second requirement of the problem asks about the angles where the contact force becomes negative, which when happens, a follower jump will occur. From the graph, we can see this happens in two different regions. The first region is between 0 and a value less than 90 degrees, because from the table the force is positive at 90 degrees. And the second region is between a value greater than 270 degrees, because again from the table the force is positive, and 360 degrees. To precisely determine the interval limits, we need to find the angles where the contact force is 0. And by equating the contact force expression to 0, we can get the following angles. And therefore, the regions can be precisely defined as: the first region is when theta is greater than or equal to 0 to a value less than 88.66 degrees. And the second region is for the values of theta that is greater than 271.34 degrees and less than or equals to 360 degrees. The third requirement asks about the preload value to eliminate any follower jumps. By writing the expression of the contact force, we want the preload value so as the contact force is at least 0 and not negative. For the term that contains theta, knowing that cosine theta ranges from -1 and 1, then the highest negative value term would be -8.573. This translates into the following equation, and by solving it we can get the minimum preload force to be added to the system to eliminate any follower jumps. Now pause the video and read question 2 before we proceed.
Open your mind. Open your mind. Not literally.
For the rise interval, we can calculate the displacement, velocity, and acceleration, where h equals to 0.02 and beta equals to 180 degrees. Using the equation of the contact force, we can get the following expression. By now, we can calculate the contact force at different angles during the rise interval. Likewise, we do the same for the fall interval, when an exception, displacement, velocity, and the acceleration are different. Therefore, we can plot the contact force as shown here. The second requirement of the problem asks if there are angles where the follower jumps occurs. And the answer of this part is no, there are no angles where follower jumps occurs because the contact force is always positive during the cycle. The third requirement asks about the preload value required to eliminate any follower jumps. And for the same reason we stated before, we don't need to change the preload value. Now for question 3, pause the video and read the question carefully.
Open your mind. Open your mind. Not literally.
Okay, the first requirement asks about plotting the lump model, and in this case the lump model is just we have concentrated mass M, which is to the spring and a damper. We have a contact force f of t in the direction shown in the figure. We have a reference datum where we can calculate our displacement, velocity, and acceleration. And for the free body diagram, we have the following forces as shown. Now, the second requirement of the problem is to calculate the natural frequency. So the natural frequency omega n equals to the square root of the k over m, the spring constant over the mass. Both of these variables are given in the problem, and therefore we have omega n with the value shown in the screen. Now, the third requirement is calculate the required damping coefficient to have a critically damped system. We have zeta equals to damping coefficient over the critical damping coefficient. And now for critically damped the system, we have zeta equals 1, which means that C equals to Cc. Now, Cc equals to 2m omega n, and we can get the value of 6.324, and therefore our damping coefficient C equals to this value. Now, for the final requirement, we need to recalculate the damping coefficient if the damping ratio equals to 0.1, and we have to specify the damping status of the system in this case. So we have zeta equals to 0.1. That means that C would be equal to 0.1 cc, which equal to this value. Now, because zeta is less than 0.1, then the system is under damped system. This concludes our tutorial, and until next time.